Okay, we're going to do another problem. So we'll do lots of problems, so you should be able to do these on your own. You are driving a car at 75 kilometers per hour, 25 over the speed limit. You see a police car slow down to 45 over a distance of 88 meters. What's your acceleration and elapsed time? Now, first of all, as soon as you read that, I mean, what's the acceleration? It's going to be negative, right? So you better get a negative answer. Okay. Now, you know, before you do anything, remember, everything has to be in MKS. So, well, let's do the motion diagram and all that, but we got to convert, right? We got to convert kilometers per hour to meters per second. All right, so, you know, normal one-dimensional coordinate system, whatever. Come on. So plus, minus, okay? How many points do we need? Well, you know, what do you think? Do we need 3 points or 2 points? I mean, what's the important part? The important part is, you know, now notice that this one doesn't say anything about reaction time, right? And so let's just put our first point when we hit the brake. And the second point is, you know, when we've slowed down to 45 kilometers per hour. So we just need 2 points. All right, so the motion diagram, you know, we're just slowing down, right? Okay, so we know that velocity is positive, but acceleration is negative. So we know we got to get a negative acceleration. Okay, all we need is, we just need 2 points, right? 2 points. So x0, v0, t0, x1, v1, t1. Okay, let's gonna start being a little bit lazy, huh? So we'll call this the origin, might as well. So we'll say x0 equals t0 equals 0. We can do that, there's nothing wrong with that. And v0 is 75 kilometers per hour. And then x1 is 88 meters. V1 is 45, right? Kilometers per hour. And T1, we don't know. T1 equals question mark. And A is question mark. Okay, awesome. All right, we got to get rid of these kilometers per hour, you know. Okay, so let's just look at, we have to do it twice, so let's just get the factor and just use it twice, right? So 1 kilometer per hour, and we got to fix it, right? So 1 hour equals 3,600 seconds, and then 1 kilometer equals 1,000 meters. So I multiply that out and get 0.2778 meters per second. So that means that 75 kilometers per hour, and you multiply that by 0.2778 meters per second divided by a kilometer per hour, right? And then you get 20.84 meters per second. And you do the same thing to the other one, and I promise you, you get 12.5. Okay. So you can do it this way, or you can just do it the other way. I mean, I don't care how you do it. I mean, you could have just, you know, you could have just done it like this, right? This is 75 kilometers per hour. 1 hour, 3,600 seconds. A kilometer is 10 to the third meters, right? You do that, and you get this. Okay, and you do the similar, and you get that. However you want to do it. Okay, let's see. What's the acceleration? All right, so first we want to get acceleration. Okay, look at those equations. All right. Well, let's see now. Do we know the time? I mean, it said first find the acceleration, right? Okay, so let's see what, I mean, look at, we know both velocities, we know the distance or the displacement, right? We know that both velocities, final and initial. We know the displacement. We don't know the time yet. So in order to find the acceleration, this is not going to help, right? Because we don't know the time. This is not going to help because we don't know the time. Hey, look at this. We know both velocities. We know the displacement. Perfect, right? Perfect. Okay, so now let's start being a little lazy, okay? So, or fast. So V1, because final is 1, right? Final is 1, initial is 0. So V1 squared equals V0 squared plus 2A delta x. Delta x, okay? All right, now what's delta x? It's x final minus x initial. So it's x1 minus x0. But what's x0? It's 0. So this is just x1. All right, so start doing stuff in your head. You don't have to do so much writing, you know? Okay, so what do we want? We want A. Well, awesome, just do it, right? So V1 squared minus V0 squared over 2x1 equals A. And so V1 squared, so there's nothing canceled, but that's okay. So let's see, where's V1? 12.5, is that 12.5? Yeah. So 12.5 meters per second squared minus V0, 20.84 meters per second squared. The whole mess over 2x1, 88 meters. I promised you, you do that, you get minus 1.58. Look at the units. We have a meter squared over a second squared on the top. We have a meter on the bottom. So the meter kills the meter squared. We get a meter per second squared. Meter per second squared. Now, this is acceleration. Okay, so we have the right units. We know it had to be negative. We get the negative. Is this sort of reasonable? Yeah, it's not like a gazillion. It's not like 0.001. It's just reasonable. All right? Okay, so A is, so A equals minus 1.58 meters per second squared. Okay, then we got to find T1. Again, see how great this is? Once you have this done, you don't even have to look at the problem anymore. Okay, so now we got to find T1. So now we want to find T1. Okay. Let's see. Well, obviously this is not going to help us, right? So that's not going to help us. Let's see. Well, you know, I guess we could use this one, right? We could use that one. But why? I mean, this would be a, you know, this would be a quadratic. That's going to be a lot of work. I don't want to do it. Use this one. I mean, we have V final. We have V initial. We have A. We can just get T. So again, you know, you could use this one, but why? You know, I mean, this would work, but you have a quadratic equation to solve. This is simple, so just choose the easy one, you know. Okay, so let's choose the easy one. So the top one. So we have V1 equals V0 plus A. Now what's delta T? Again, delta T is T1 minus T0, right? Final minus initial. T0 is 0, so it's just T1. So we just have A T1. Okay, we're trying to solve for T1, so just do it. So V1 minus V0 over A is equal to T1. So V1 is 12.5. V0 is 20.84. Don't forget your units. A is minus, right? Minus 1.58 meters per second squared. It better be minus, right? We're trying to find a time. If the numerator is negative, we better have a negative acceleration, right? Or we're going to have negative time. And so you do that, and you come up with 5.28 seconds. Okay, right? Because we have a meter per second. Look at on the top, we have a meter per second. On the bottom, we have a meter per second squared. How do you divide fractions? By flipping and multiply. So you get a meter per second multiplied by second squared over meter. Goodbye, 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 goodbye. So we get seconds, all right? Okay, we get the right units. This is positive. It seems like a reasonable number, 5 seconds. So we believe it. Okay, that's how you do it. Okay, very good. Now, I don't want to do that. Okay, I'm not going to do this one. I just want to kind of just give you kind of a hint. So let's read this. A sprinter accelerates at 2.5 meters per second squared until reaching his top speed at 15 meters per second. He then continues to run at top speed. How long does it take him to run the 100-meter dash? So I think this one, the motion diagram is really important. I'll show you why. Okay, so what does it say? It says, I'll just write it here, right? It says he accelerates. Oh, let me just do a bit of that. Whatever. Okay, so so A0 is positive, right? All right, he accelerates, but then what does he do? So he gets his top speed at 15 meters per second, and then he continues to run at that top speed. So here, oh gosh, I gotta do this right? All right, so here, call it A1 is 0, right? Now remember, you can only use kinematic equations for constant acceleration. So what you have to do here, you have to work this problem separately, then you have to work this problem separately, because you have two different accelerations. You can only use kinematic equations if you have constant acceleration, right? So you have to do this first, then you have to do this. So it's two problems for the price of one. All right? So, you'll have stuff like that. But again, it's not a big deal, It's just two problems. It's just two regular problems, all right? If you know how to do one, you can do two, right? So just kind of be aware of that, all right? Okay. Go away. All right. Okay, so this is what we've done. We differentiated clearly between position, velocity, and acceleration. We can interpret kinematic graphs. We can translate kinematic information between verbal, pictorial, graphical, and representations. We know what instantaneous velocity and acceleration are. We know how to do area under the curve integrals, free fall. We'll still talk about free fall. We just talked about it in one dimension. We've got to talk about it in 2 dimensions later on. And we learn how to solve problems. Okay, so here it is, right? For free fall, the acceleration due to gravity, you call it minus g, minus 9.8 meters per second squared. G is positive. If somebody gives you the velocity and the time, you can figure out where you end up. This is true for constant velocity. This is true for any velocity. And remember, this integral is just the area under the curve. You should have learned that in calculus, right? So the v delta t is this. And you can use the same equation for velocities, right? Start with a velocity, you accelerate for a certain time, you end up with a different velocity. This is true for constant a, this is true for varying a. We almost never have varying a, by the way. We always have constant a, right? Because we want to use our kinematic equations. Not until much later. All right, these are definitions. You just got to know these definitions, right? Got to know these definitions. These are the kinematic equations. Got to know those. You got to know how to do a pictorial representation, how awesome it is. And that's it. Thank you very much.